Today we are going to discuss the language accepted by PDA, and we are going to prove that language accepted by final state and empty stack are same. That means if you have a PDA and that PDA is accepting a language, and a language is said to be accepted by a PDA, that is, as you have a finite control, a stack, and this is the input. As an input W is printed on the tape, and this finite control will be initially in state Q0, and initially this is having this stack is having Z0 on top. This is the bottom of the stack marker, and this is starting. That means starting from Q0, if it reaches QF, one of the final states, and when you are processing this, after reading all the input symbols of this W, if it reaches QF, and QF is a member of one of the final states, here Q sigma tau delta Q0 Z0 F, here F is the set of final states. F is a set of final states, and initially you are starting from Q0, and if you are able to reach, or if the finite control reaches one of the final state, then that thing can be accepted. That means when you reach this place, then you are not bothering about what are the contents of this. That means you have a set, and this is maybe gamma, that is represented by gamma. That means that is language accepted by final state, means you are starting with state Q0, and after accepting, or after reading all the inputs and processing it, if you reach a final state QF, then that string can be accepted. At that point in time, we are not bothering about the contents of this stack. That is why here an instantaneous description, initially Q0, that means T of M. Language accepted by final state is represented by T of M. Language accepted by M by final state is all strings W such that Q0 W is at 0. That means Q0 is the start state, and input symbol you have to process is W, and this is on top of the stack Q0 W. That means after consuming all the input symbols, that is why we have put epsilon here. That means here you have to process W, and here nothing has to be processed, and the states changes from Q0 to QF, and now current stack content is gamma. Gamma means we are not bothering about what are the contents of the stack, and if you are able to reach one of the final states, then that string can be accepted. That's the main. Now, what is language accepted by empty stack? Here in this case, we are not bothering about the content of the stack, and here in this case, we are not bothering about the content, or we are not bothering about the final state, and here the one and only condition is there. After processing this, here see, Q0 is the start state and QF is final state, and now we are not bothering about the final state, and one thing is, after processing this, it should empty the stack. That means we are starting with Q0, we are not bothering about this Q, and after processing this W, when it reaches on a state, after this we are not bothering about the state. Here suppose that Q belongs to Q, this Q belongs to any one of the states Q, but we are going to consider this. That means if this is emptying the stack, that can be accepted. That means if it is emptying the stack, that can be accepted. That means language accepted by empty stack is represented by N. That means T means it is language accepted by final state, and N means language accepted by empty stack. And N of M is equal to W such that W means the set of strings W such that Q0 W sub 0. That means initially the finite controller will be in state Q0 and the input you have to process is W and current top of the stack is Z0. In one or more states it reaches Q epsilon epsilon. That means this Q, any Q it can take. That means any value of state, and you have consumed all the inputs and the current of the stack is empty. That means you have processed all the, or you have emptied the stack. That means upon processing an input symbol, if it is empty in the stack, that means that can be accepted. So language accepted by a PDA can be language accepted by final state or language accepted by empty stack. Language accepted by final state means in that case we are not bothering about the content of the stack, and in that case you have to reach the reach one of the final states after processing all the input. Language accepted by empty stack means in that case we don't have any final states. We are not bothering about the after processing the input symbol W, it reaches a state, and we are not bothering about the state, but we are going to verify the contents of the stack, and if the stack is empty, that means that can be accepted. So there are two cases: language accepted by final state and language accepted by empty stack. And this is language accepted by final state we usually represent by T of M, and language accepted by empty stack is N of M. So both of them are equivalent. That we are going to prove. We are going to prove the equivalence of language accepted by final state and language accepted by empty stack. As I told you, language accepted by final state means upon reading an input, that means here you have an input W. This is input W, and initially that will be in state Q0, and after processing this you reach one of the final states, and initially you have Z0 on top of the stack, and after this we are not bothering about the content size. Z0 is there. Here gamma, a set of symbols may be there on the stack, and we are not bothering about the contents of the stack. That means here Q0, initially that will be in state Q0, the input is W, and current of top of the stack is Z0. In one or more steps that reaches final state UF, all your inputs have been consumed and we are not bothering about the content. Gamma is at 0. That means the stack is not empty and it reaches one of the final states. That is M1. That is language accepted by final state. And M2, we have a language accepted by final state M2. This is M2. And here you have a set of states. Sigma is the input string, tau is the stack alphabet, delta 2 is a transition function. Delta 2 is a transition function, Q0 the start state and Z0 the bottom of stack marker, and F is a set of final states. And this is accepted. This is accepting if Q0 W on Z0 in one or more steps it reaches this. That means QF the final state. Now this is M2. That means initially that will be in state Q0 and the current of the stack is Z0, and now you have to process this input W, and upon processing that it reaches one of the final states and you have consumed all the inputs and we are not bothering about the contents of the stack. So we are going to prove that if you have such a PDA M2, you can have another PDA M1 which is accepting the same language by empty stack. Okay. Now we are going to have this is if L is equal to T of M2 for a PDA M2. That means T means this is accepting by final state. If you have a language which is accepted by final state, there exists an equivalent finite automaton M1 equivalent push down automaton M1 which is accepting the same language by emptying the stack. So we have the proof of this is, first of all, you assume that this is a PDA which is accepting a language by final state, and from this you are going to develop or you are going to construct a new push down automaton which is accepting the same language by emptying the stack. For that, I am going to have a new push down automaton which is having the same states, plus you are going to have two more states. That means here I am going to have, this is W, and you are going to have two more states, Q0 dash and QE. Here you have two more states. That means initially this will be in state Q0 dash. Here the original M2 has Q0, and here the start state is Q0 dash, and Q0 dash, and you have another state QE which is an erasing state. QE which is an erasing state that I will tell you about that. Now sigma is same for both of this, and tau union x0. Now you are going to have a new stack symbol. That means now I am going to have a stack here. For this M1, you have another stack, and the bottom of the stack marker is x0. So here we have one more symbol added to original tau, that is x0, and delta 1 is a transition function. Q0 dash, here a new state you have added which is the start state. This is the bottom of the stack marker. You have just added x0 to this tau, that is the bottom of the stack marker, and we don't have any final states now. That means that's why here I am having 5. So how this simulation is done, that we are going to discuss. That means delta 1 of Q0 dash epsilon x0. That means if the current input symbol is Q0 dash, or current state is Q0 dash, and current top of the stack is x0, without writing any input, this will switch to Q0. That means at this point itself it will move to Q0. That means delta 1 of Q0 dash epsilon x0. If the current top of the stack is x0, and if the current state is Q0 dash, and current input symbol is x0, without writing any input, the current state is changed to Q0. Now it is Q0 and Q0. Okay, that means without reading any input, it has changed to Q0. Now delta 1 of QA is equal to delta 2 of QA is for every Q element of Q, A element of sigma and Z element of tau. That means delta 1 is same as delta 2 if Q is an element of Q, tau is Q is an element of Q, A is an element of sigma, and Z is an element of tau. That means if QA is from M2, then delta 1 is same as delta 2. That means it will make the same moves as that of this, and it reaches one of the final states QF. Definitely that will reach QF, and at this point in time, this will have Z0 and gamma. That means same as that of M2. Now if Q is an element of F, here after processing this up to this point, this is same as this M1 is same as M2. Only difference is the initial start state is Q0 dash for M1, whereas Q0 is for M2. But without accepting anything, it switches to Q0. That means the start state is practically it is Q0 itself. Okay, so this will make the same moves. M1 will make the same move as that of M2, and it will reach final state QF. And when you are reaching this QF, this stack contains what? This is instead of z0 you are going to have x0 at the bottom, and above that you have z0 here, and here also you have z0 here. Why? Delta 1 of q0 dash epsilon x0, that means f0, if x0 is on top and q0 dash is the start state, then when you are converting that to state q0, you have pushed this z0 onto the stack. That means when you are starting this q0, z0 is not on the bottom of the stack, actually x0 is on the bottom of the stack. That is the only difference between this and this. The only difference lies in here, instead of s0, here x0 is on the bottom, and just above that you have z0. And after that, when you are processing this same steps, you reach qf, and once you reach qf, that means if q is an element of f, delta 1 of q epsilon is contains epsilon qe epsilon. That means if after processing all the inputs nothing remains, that means epsilon remains. You have all the input symbols have been processed, and after that, if qf on epsilon and if current top of the stack, whatever it is, current top of the stack, you are going to erase that. That means q1 q epsilon is contains qe epsilon, means qf changes to qe, and in this state qe you are going to erase this and erase all this. Okay, this state qe for erasing all this, and qe epsilon is set. That means qe epsilon contains qe epsilon for all z element of z element of tau union x0. That means now once it is transformed to the state QE, it is erasing the contents of the stack. That means now the stack is empty. That means that can be accepted. That means if you have a PDA which is accepting a language by final state, there is an equivalent finite automaton, push down automaton, which is accepting the same language by emptying the stack. Now we are going to have another theorem, that is, now we have a language accepted by final state and there is a equivalent push down automaton. We have converted that to a push down automaton which is accepting a language by empty stack. Now the next part of this proof is, if you have a push down automaton which is accepting a language by emptying the stack, we have to prove that there exists a push down automaton which is accepting the same language by final state. Now the second part of the proof is, this is the theorem. If L is equal to n of m1, that means this is accepting by empty stack, and n of m1 for some PDM1, that means PDM1 is accepting by empty stack, and there is an equivalent push down automaton which is accepting the same language by final state. That means that is m2. That means here initially this is accepting by emptying the stack, empty stack. That is why here you have 5, and this is accepting the final state. That means here we have qf. That means this is accepting by final state. Say m1, from m1 how we can generate m2? Initially, suppose that this is your input w, this is the input string w, and initially we have the state q0 and current top of the stack is having say z0, and upon processing this is reaching a state, and after reaching here this is emptying the stack. That means the stack is empty, stack empty. Okay, this is emptying the stack, and q0, start state is q0. Upon processing this, it reaches a state emptying the stack. That's why it is accepted. here q sigma tau delta 1 q0 z0 and phi. For processing w, if the stack is empty, that string is accepted. And this is m1, this is m1. Now we are going to simulate m2, which is accepting the same language by final state, For that, here this is the input w, and initially the start state is q0 dash. We are going to have new states q0 dash and qf for final state and q0 dash for start state. And initially the stack is having, we have added one more symbol to the stack, that means an extra symbol you have added to the set of stack symbols, which is x0. Initially we are having x0 on the stack. Here you have z0 on the stack, and we are starting with q0. Here we are starting with q0 dash, and now you have the bottom of the stack marker x0, and q0 dash. If the current state is q0 dash and current top of the stack is x0, what will happen? This will switch to a state q0, and you are going to add z0 here. That means you have added z0 on the top and you have switched to q0. Now this is q0 z0. This is this condition. That means after this, whatever this m1 do, here also we are going to do that. That means q0 on x0. That means all the simulations here, whatever is done in m1, that you are going to do in m2, and you reaches a state q. This is the state, and up to, that means stack empty means up to z0 you have to empty. That means what remains here? Here x0 will remain. X0 will be on top of the stack. And once you have q as the start state and no more input symbols are there, and x0 is on the top of the stack, what will happen? It will switch to a state which is qf erasing this stack. Erasing the stack means this stack will be empty. That means here that will switch to a new state. These are the things, or these are the delta to transition. That means q0 dash on accepting x0. That means if the current top of the stack is x0 and if the current state is q0, without reading any input symbol, it will switch to q0, and you have pushed z0 on the stack. That means q0 z0 x0. That means this state. And after that, delta 2 of QAZ includes delta 1 of QAZ for all QAZ belong to M1. If for all QAZ which are belonging to M1, this is same as this. That means it reaches Q, and up to Z0 it will wipe out. That means up to Z0 it will be empty. That means what remains is X0. And what is delta 2 Q epsilon X0? That means no more input is there, q, whatever be q, no problem. But if x0 on top of the stack, you have to switch to a new state qf, and that is this one for all q element of q. That means here you have a push down automaton m1 or any push down automaton which is accepting a language by emptying the stack. There is an equivalent automaton which is accepting the same language by final state. And in this proof, you have two parts. First portion is if you have a push down automaton which is accepting a language by final state, there is an equivalent automaton you have to construct which is accepting the same language by emptying the stack. And the second part of the proof is, If you have a push down automaton which is accepting a language by emptying the stack, you have to construct an equivalent finite automaton which is accepting the same language by final state. Okay, thank you.